Hey everybody, welcome back. Happy weekend. I wanted to record a quick video talking about one of the homework problems. There was a request from a couple students just to talk through this particular problem. And yeah, I think it's a great and slightly challenging problem. I wanted to talk a little bit through my thought process. And the problem was this. It was the second one from the homework. So it was, let's take a continuous function, f of x, at least it's continuous at a specific point in the domain, x equals c, and we're assuming that f of c is positive here. Then we are asked to show that there exists two numbers, an alpha and a delta, both bigger than 0, such that whenever x minus c is less than delta, we get that f of x is bigger than alpha. Okay, so here is the idea behind this problem. At least this is sort of how I'm picturing it in my head, building intuition. So I'm going to just sketch an f of x. It doesn't have to be a positive function always, but it at least has to be positive, let's say something like that, at our point c. So f is a function that's continuous at c, and it's got, let's say that is c, and we're assuming that f of c, that's this point right here, is positive. Okay, so the question becomes, show that there exists an alpha and a delta such that when x minus c is less than delta, aka when we are in, right, so aka, this is the same thing as saying when x is an element of the delta neighborhood around c, we get that f of x is greater than alpha. And so then the idea is that alpha is going to be some number, right? But it's sort of representing a height. So maybe let's pretend this is our height alpha. And if I just sort of examine that height, maybe I'll just draw a line here to signify what the height is. If I just examine that height, then there should be a little delta window right around C. Maybe this is my delta window or my delta neighborhood, such that whenever I'm plugging in an x value that's right around c that is in that delta neighborhood, whenever x is in that delta neighborhood, we have that the corresponding height f of x must be bigger than alpha. In other words, the x values that I plug in here must fall above the height alpha. And intuitively, I mean, based on this intuitive picture, this seems like this will be the case, right? Intuitively, if I'm marking my f of c as positive, then there has to be at least a little wiggle room around here where it stays positive, right? Where my function stays, in fact, quite positive, positive enough to be above alpha. And as we said in the prompt, we will often call this being bounded away from 0 or bounded above 0. So in this little window, if c is positive and f is continuous, there should be at least a little window in here where our function is bounded above alpha. Now, to rigorously show this, though, we have to think a little more critically about the structure here, right? We know that f is a continuous function. And so because we know that f is continuous, we know, maybe I'll call this, we'll begin the proof, right? Just sort of listing what we know. We're going to say, let f be continuous at c. At x equals c. What that means, right? That means that for every epsilon, there exists a corresponding delta such that, let me fix that delta, right? There exists a corresponding delta such that whenever f of x, or whenever, I'm sorry, x minus c is less than delta, f of x minus f of c, absolute values, is less than epsilon, right? So this is a fact that we know, and this fact holds true for every epsilon, right? So for no matter what epsilon we plug in, we know that there exists a delta so that the rest of the statement holds true. Now this structure of continuity that we are allowed to assume is true is really going to be the backbone of the proof. Because our function is continuous, we know that something holds true for every epsilon. And so if we choose a specific epsilon, sort of a cleverly chosen epsilon, then maybe we can get somewhere. We can say something nice, something definitive. So because this holds for every epsilon, let's think about what a good epsilon to choose might be. And I'm going to erase just a little bit of my picture. Let's erase that line for a moment. Let's see if we can erase. Oh. Okay, so we erased the little delta neighborhood there as well. We've still got our point C, which is right here. Okay, so remember, this statement about continuity is a statement that says if I choose an epsilon, then I can find this delta and this, such that whenever we're in this delta neighborhood, our output values f of x will always be within a distance epsilon from f of c, right? So what we have here is we actually have our statement of continuity is implying something about the height f of c. And let's mark off where that is on our picture. Just getting the right tool here. So according to the height, that right there seems to be our f of c. Right, so f of c is at that height. And then our statement about epsilons and deltas, right, is saying that if I choose an epsilon, i.e. a tiny little epsilon window or an epsilon neighborhood around f of c, there's a corresponding delta window or delta neighborhood around c, such that x values in that neighborhood will map to f of x values inside of this neighborhood. And here's where we gain some intuition on how we can use and choose a clever epsilon. I'm trying to prove that such an alpha down here exists and that our function will eventually stay above alpha as long as I'm close to the point C. If I choose an epsilon small enough so that my epsilon window, drawing over here on the height, if my epsilon window here stays above 0, so let's say that I let epsilon be some number up, some small enough number to make sure that this epsilon window stays positive, then eventually there'll be a corresponding delta window down here in which all of my x values have f of x values popping up into here, and therefore my f of x values will be positive, and specifically they will be bigger than some alpha, which I have sort of designed down here. So that's really the big idea. This statement holds true for every epsilon. Let's just make sure that epsilon is so small that when I'm able to say this definitely holds true, that will mean that my f of x values stay nice and tall up here. Okay, and so that's going to be our big strategy here. And now let's get into the specifics. So we just have to make sure that our our epsilon is small enough so that that epsilon window stays positive. And my hint for doing this, or a good strategy for doing this, not the only strategy, but a good strategy for doing this is let's fix a given small epsilon, and let's fix epsilon to be equal to f of c divided by 2. Now here's my reasoning for doing this. I'm going to erase some of this stuff over here really quickly. Perfect. Okay, here's my reason for doing this. F of c is some positive number. We don't know how big it is, but we know that it's positive. And so f of c divided by 2 will also be a positive number. Furthermore, when this distance right here is f of c over 2, this distance right here will also be f of c divided by 2, right? In other words, f of c over 2 is exactly half the distance from the x-axis as f of c, and therefore, when it comes time to create my epsilon neighborhood, right, my epsilon neighborhood of f of c will go down exactly halfway towards the x-axis, right? And so this entire neighborhood right here, that is my epsilon neighborhood of f of c. And by choosing epsilon in this manner, I'm guaranteeing that that epsilon neighborhood stays above the x-axis. Okay, great. So let's fix epsilon to equal f of c, right? Then we know that there exists a corresponding delta. And maybe I should say this. There exists a corresponding delta. Let's jump back to blue. Then there exists a corresponding delta such that if f of x, or I'm sorry, if x minus c is less than delta, f of x minus f of c is less than epsilon, right? So it's less than f of c over 2. And that's great. We know that that's true by the fact that f is continuous, right? This similar statement would have held true for any epsilon, so it holds true for this epsilon. Now, all we have to do is make the observation that visually, geometrically, if f of x minus f of c is less than f of c over 2, that means that our f of x values are in this range, which means that they can get at most half the distance to the x-axis. And in particular, they're definitely positive. Not only are they positive, but they are bounded above this line. And so this actually gives us a way to figure out what a good choice of alpha will be as well, right? They're bounded above that line. And so with alpha equal to f of c over 2, right? Or really we could choose any smaller positive value as well. But the fact that our f of x minus f of c's will be less than f of c over 2 means that our f of x's will be bounded between these two heights, which means that our f of x's will be bigger than this height right here. And so we can conclude by saying if we let alpha, by letting alpha equal f of c over 2, or any smaller number, or any smaller positive number, right? We know that f of x will be bigger than alpha when x minus c is less than delta. Right, and that's just going to be true by the geometry of this picture and interpreting visually what it means for this to be true. So that was really the argument in a nutshell. It comes down to exploring the notion of what it means to be continuous at the point C and coming up with this sort of geometric argument, right? That if we make our epsilon small enough, for example, f of c over 2, then having this restriction will necessarily imply a restriction that looks like this, just from the geometry of where these points all sit on the real number line. So I hope that was helpful in clarifying this problem. Sort of a tricky but fun problem that really requires you to think a little bit geometrically about what's happening. Let me know if you have any questions about this, and have a great rest of your weekend.